Okay, we're 9.10 now. Let's see, 9.10, and I've got a copy here, handout. And basically what this theorem says is that if your series converges to f of x, then the coefficients must be Taylor coefficients. So if you have a series and it's convergent to a function, then it must be, the coefficients must be Taylor coefficients. So it must be what we would call a Taylor series. Okay, so what we're going to do is use this to form the cosine. So, okay, so let's say we're given, example 1, we're given that f of x is cosine. So we're going to form a Maclaurin series and then determine the interval of convergence for that. Okay, so this will be a power series using the Taylor coefficients, basically. And we'll start with f prime, which is negative sine, double prime, be negative cosine, triple prime, be, we have sine, and fourth derivative would be cosine, fifth derivative, negative sine, sixth derivative would be negative cosine. And now evaluating in here, if it's Maclaurin series, we're going to evaluate about 0. So this would be 1. F prime of 0 would be 0. Double prime of 0 is a negative 1. Triple prime at 0 is a 0. Fourth derivative at 0 is 1. Fifth derivative at 0 is a 0. And the sixth derivative will stop there. I think it's going to be pretty easy to see the pattern here with these coefficients. So what we have is this series now. We'll start off with, well, in general, you'll have f of 0 plus f of 0, 1 factorial, x to the 0, f double prime, oh sorry, it's f prime of 0, f double prime 0 over 2 factorial with an x squared, and so forth. So what we get is, we'll put in our numbers here, we'll have a 1. Skip this one, it's a 0. Next one, whoops, that would be a minus. Okay, so a 1 minus x squared over 2 factorial, and plus, the next term would have been a 0. We just keep alternating there, so we'll have a plus x squared over 4 factorial. The next term would have been a 0, the fifth derivative, and then the next term, oops, that's a 4 there. And then that's a 6, a 6 factorial, and it would keep going like that. Okay, now, so we can see that this could be generalized like so. We've got an alternating sign, and we have an x to the 2n with a 2n factorial. Okay, now you can check the in this case, we want the interval of convergence, so let's check that. First of all, we find that limit of that ratio. This would be this limit. We'll have, I'll ignore the negative signs here. We'll just have this x to the 2n plus 2, 2n plus 2 factorial times 2n factorial, and then you've got the x to the 2n down here. Okay, and that comes down to, looks like we just have an x squared up here. And this 2n factorial, you're going to see that actually comes down to, you lose the first, we'll have a 2n plus 2. And the next factor is a 2n plus 1. And the next factor, which would be a 2n factorial, would cancel with this factor in the numerator. So this is all we have so far. Okay, now that limit, as you can see, is 0. So that means this one will have infinite radius of convergence, and therefore our interval of convergence, I of c, will be negative infinity to infinity. So what we have here is this series, and it represents the cosine of x, and it will converge for any x on this interval, any value of x. So now, what the theorem does not say is that we still don't know if this series that we have converges to the function cosine of x. We do know that if remember what the theorem says, it's if the series converges to f of x, then the coefficients are in this form. So we have a series represent the function, but we don't know if it actually converges to that function for all x. I'm not sure about that. That has to be determined. We'll talk about that idea next.